Yes, this is G.K. Raghavan, chemistry faculty from All Force College. So I welcome you for All Force Chemistry e-learning program. So in this session 9th, today we'll discuss about concept of hydrogen spectrum. Concept of hydrogen spectrum. The session 9th is the concept of hydrogen spectrum. The spectra is, simply we can define, it's a group of light or group of wavelengths. Hydrogen spectra, that is, now small quantity of hydrogen gas is taken in the discharged tube. The small quantity of hydrogen gas is filled in the discharged tube. So all these are the hydrogen molecules. In the gaseous state, hydrogen is present in the form of H2 molecules. All these are H2 molecules. That is, hydrogen gas is filled in the discharge tube under low pressure, and by passing the potential current, the gas is heated. Small quantity of hydrogen gas is filled in the discharge tube. Under low pressure, the gas is heated. Some part of the energy is absorbed by the hydrogen molecule to dissociate into hydrogen atoms. Molecule is dissociated into atoms. Hydrogen molecule is dissociated into hydrogen atoms. And we know that each hydrogen atom has one electron because hydrogen atomic number is 1. So every hydrogen atom has one electron in its shell. Okay, next, the remaining energy is absorbed to excite the unpaired electrons of hydrogen atoms. To excite unpaired electrons of hydrogen atoms. Again, small amount of hydrogen gas is filled in the discharged tube. Under low pressure, the gas is heated to high temperature. Some part of the energy is absorbed to dissociate hydrogen molecule into atoms. The other part of the energy is consumed to excite unpaired electrons of hydrogen atoms. So, by absorbing some photon energy, the electrons get excited into the various energy levels. Okay, that is the excited electrons. The excited electrons, see, for example, to this electron, say it is one electron, to this electron, when I am supplying some amount of energy, the electron jumps from lower energy level to higher energy level. That means the electron, when it moves into the higher energy level, it is being unstable. That means it is coming back to the ground state. That means the excited electrons should get de-excited into the ground state, that is normal state. Okay, that is during de-excitation process. During de-excitation process, say for example, shells and say 1, 2, 3, 4, 5 shells. The excited electron is present in the, for example, 5th energy level. So, being it is unstable at the higher energy level, wherever it may be, higher energy level, the electron being unstable, it should come back to the normal state, that is ground state. So, the de-excitation process of the excited electron may takes place directly in one step, or the electron may get de-excited into several steps. It may de-excited into several steps. The excited electron get de-excited. The de-excitation process may takes place directly in one step or in several steps. It may be several steps, but finally it should come to the ground state, that is normal state. So that is a de-excitation process. During de-excitation process, that means when electron is jumping from higher energy levels to lower energy levels. That is, in every stage it emits some energy. During de-excitation process, the radiation is emitted. The emitted radiation is passed through a prism. The dispersed spectral lines are noted on the photographic plate. The dispersed spectral lines are noted on photographic plate is called hydrogen spectra. Okay, that is a detailed explanation of the definition of formation of hydrogen spectra, but in short we can define the hydrogen spectra like the spectra obtained from the emission radiation, the spectra obtained from emission radiation of the excited electrons, emission radiation of excited electrons of hydrogen atoms, gaseous hydrogen atoms is called hydrogen spectra. The spectra obtained from the emission radiation of excited electrons of gaseous hydrogen atoms is called hydrogen spectra. That is a simple way we can define hydrogen spectra like that. Okay, now another point is hydrogen spectra is the simplest atomic spectra of all elements. Hydrogen spectra is the simplest atomic spectra of all elements because hydrogen atomic number is 1, it contains only one electron. So we can find the spectral lines in hydrogen spectrum that is due to one electron. Okay, so that is element to element, as atomic number varies, the number of electrons varies and the spectra is also different. Okay, so therefore we can say hydrogen spectra is the simplest and it is atomic spectra because it is obtained from gaseous hydrogen atoms. So it is simplest atomic spectra. And another point, it is obtained from the emission radiation, therefore hydrogen spectra is emission atomic spectra. Okay, it is emission spectra and atomic spectra, right? So this is definition of hydrogen spectra, right? Hydrogen spectra when observed, that means the photographic plate obtained from the emission radiation, that is spectra of hydrogen. So that photographic plate observed by different scientists, so they discovered different series in the hydrogen spectra. So hydrogen spectra consisting of 5 series of spectral lines, hydrogen spectra consisting of 5 series of spectral lines, namely Lyman series, number 2 is Balmer series, Lyman series and second Balmer series, third one Passion series, fourth is Bracket series, and fifth one is Fund series. So you should remember all these series because this explanation of the hydrogen spectra is very important for long answer question for IPE examination. It is very, very important long answer question. Okay, explain, that is what are the important postulates of Bohr's atomic model, and explain hydrogen spectra. That is very important IPE question, and from this, so it is some important theory points as well as the numericals are important for your competitive examinations like EAMCET, mains, okay, and other examinations. Okay, how many series found in the hydrogen spectra? So in hydrogen spectra, 5 series of spectral lines are found. What are the names? So Lyman series, Balmer series, Passion series, Bracket series and Fund series. Why these spectral lines are formed? See, in the hydrogen spectra, when de-excitation of the electrons takes place, the de-excitation process may involve the electron come down to the ground state directly in one step or in several steps. Okay, during this de-excitation process, some amount of radiation is emitted. The emitted radiation is passed through a prism. The splitted the dispersed spectral lines are drafted on photographic plate, that is called hydrogen spectra. Okay, so contain hydrogen spectra consisting of 5 series of spectral lines. Okay, now, so these are all the name of the different scientists: Lyman scientist, Balmer scientist, Paschen scientist, Brackett scientist, and Fund scientist. These are all the names of the scientists, and they discovered the spectral lines in the hydrogen spectra. Now let us see the simplest atomic spectra diagram of hydrogen. Atomic spectra diagram, that is 5 series. See, out of this, that is in addition to this 5 series, there are one more series is there, Ampere series. Ampere series is not published in our textbooks. That is why I am not connecting to that Ampere series. So as per our textbook information, I am discussing about hydrogen spectra. Okay, I am not discussing about Ampere series. Right. So the spectral diagram appears like this. See, this is the excited state, that is. So now this is higher energy level. Next, let us maintain gradually the distance between the spectral lines. Gradually let us decrease. Gradually let us decrease the gap between the spectral lines. So 1, 2, 3, 4, 5, 6, 7. Let us draw some more. Yeah. So these are the few spectral lines, that is few orbits we have drawn. So that is first orbit, say it is n is equals to 1. First orbit, it is second energy level, and this is third energy level, and this is n is equals to 4, fourth energy level. Okay, and n is equals to 5, n is equals to 6, n is equals to 7, n is equals to 8, n is equals to 9. Okay, these are the spectral lines. Okay, now 5 series of spectral lines. First, see, according to our textbooks, the first series of spectral lines observed by Balmer scientist, he discovered a series of spectral lines in the visible region of hydrogen atomic spectra. So that first series discovered in the visible region is Balmer scientist. Okay, so now let us go through from the beginning, that is from Lyman series onwards. Okay, so now the excited electron may be at 9th orbit, or it may be at 8th orbit, or it may be 7th or 5th or 4th or 2nd, whatever it is. When excited electron jumps from higher energy level to n is equals to 1, when an excited electron transition takes place from higher energy levels. So where it is coming? It is coming down to first orbit. It is coming to first orbit. So above the first orbit, all are we can consider as excited levels. So the excited electron jump, that is transition takes place from higher energy levels to first energy level. Higher energy levels to first energy level. Higher energy levels to first energy level. So it is coming from 9th orbit to first orbit, and 4th orbit to first orbit, and 2nd orbit to first orbit. Okay, the electrons are coming from higher, that is excited states, higher energy levels to n is equals to, that is nth orbit to n1, that is first orbit. What is n? N is excited state. It is excited state. Excited state. So from any excited state, if the electron jumping into the first orbit, the emission radiation of the corresponding spectral line, okay, should be listen carefully. the emission radiation of the corresponding spectral line. That means during this transition, when the electron is touching at first orbit, so it emits some light. So the emitted light when passing through the prism, the spectral line was found in. The spectral line was found in. The emission radiation of the corresponding spectral line found in ultraviolet region, that should be remembered, UV region of hydrogen spectra. UV region of hydrogen spectra. The series of spectral lines are named as Lyman series. They are named as Lyman series. Lyman series. That is Lyman series, formation of Lyman series. Once again listen. When excited electrons jumps from higher energy levels to n is equals to 1. Higher energy levels to n is equals to 1. From any higher energy level, it may come from any higher energy level. It may be second orbit or third orbit or sixth orbit or ninth orbit, whatever it is. When it is touching at the ground state, that is at first orbit, the emission radiation of that corresponding spectral line was found in UV region of hydrogen atomic spectra. Okay, the spectra, the hydrogen spectra is consisting of 3 regions in the spectra, that is on the photographic plate. We can divide into 3 regions. One is UV light, because we can find the lines only in the ultraviolet light. Some lines we can find with naked eye, and some lines we can identify under ultraviolet, that is infrared radiations, right? So these lines can be identified under, that is in the infrared, that is ultraviolet region. The series of spectral lines named as Lyman series. Okay, Lyman series. Is it clearly understood? Lyman series. Okay, once again, when excited electrons, transition takes place from higher energy levels to n is equal to 1. The emission radiation of the corresponding spectral line observed in the ultraviolet region of hydrogen atomic spectra. Okay, region is to be underlined. The series of spectral lines named as Lyman series. Done. It is very simple. Okay, now coming to the next one. When excited electrons, now we are going to describe Balmer series. When excited electrons, I am taking the excited electron, transition takes place from higher energy levels to second energy level. Higher energy levels to second energy level. So I am drawing with different colors, because we can see all the different colors of the spectral lines, because all these spectral lines are visible. That means we can identify these spectral lines in the visible region of hydrogen spectra. So we can identify them in the visible region of hydrogen spectra. Visible region of hydrogen spectra. Yes, all these spectral lines are forming at second energy level. That means when excited electron jumps from higher energy levels to should remember this, higher energy levels to second energy level, higher energy levels to second energy level. Okay, should remember clearly, when excited electron jumps from higher energy levels to second energy level. Okay, so after the second energy level, definitely it will come down to first energy level. Okay, when it is touching at first energy level, where we can identify that spectral line will be identified only in the ultraviolet region. That gives your Lyman series. Already we had the discussion. Now any excited electron is directly comes to the second orbit, or it may come in different stages to the second orbit. Okay, it may come directly or it may come in several steps. Okay, so if it touches its second orbit, the emission radiation of that spectral lines are observed in visible region of hydrogen spectra. Visible region of hydrogen spectra. Visible region of hydrogen spectra. The series of spectral lines are named as Balmer series. Balmer series. Balmer series. Okay, that is, what are the excited levels? Excited levels are 3 and above orbits are all excited levels. So Balmer series is formed at which ground state? So for Balmer series, the ground state is formed at second energy level. So Balmer series, for Balmer series we can say ground level for Balmer series is second orbit. Okay, any excited electron jumps from higher energy levels to second orbit. That to be remembered. That is visible region, the spectral line observed in the visible region of hydrogen spectra. Okay, and the series of spectral lines are named as Balmer series. Okay, so Lyman series, when excited electrons coming from the higher energy level to n is equal to 1, and for in Balmer series, the higher excited electrons are coming from higher energy levels to, it is coming to second energy level, Balmer series. Okay, observed in the visible region of hydrogen spectra. Okay, done, and the series is named as Balmer series, like this. Now, similarly, when excited electron jumps from higher energy levels to third orbit, like this. When excited electron transition takes place from higher energy levels to third energy level, the emission radiation of the corresponding spectral line, was observed in near infrared. Okay, so they are observed in near IR, infrared, near infrared region of hydrogen spectra. The series of spectral lines are named as Paschen series. They are named as Paschen series. They are Paschen series. Paschen series. They are named as Paschen series. So where the Paschen series is observed, it was observed in near infrared region. I repeat once again, listen. Okay, when excited electron transition takes place from higher energy levels to third energy level, that is n is equals to 3. Okay, n is equals to 1, Lyman series, n is equals to 2 for, that is Balmer series, n is equals to 3, Paschen series. Paschen series is formed. Okay, once again, when electron jumps from higher energy levels to n is equal to 3, the emission radiation of that corresponding spectral line were observed in near infrared region of hydrogen atomic spectra, and the series of spectral lines are named as Paschen series. Okay, and similarly, so the excited electron transition takes place from higher energy levels to fourth orbit, that is fourth energy level, n is equals to 4. The series of spectral lines were found in the middle infrared region. They were identified in middle infrared region. Okay, it should be remembered, middle infrared region, okay, of the hydrogen spectra. The series of spectral lines are named as bracket series. They are named as bracket series. bracket series. Okay, near infrared is Paschen series and middle infrared is bracket series. Similarly, when excited electron transition takes place from higher energy levels to n is equals to 5. Okay, so the electron transition, that is jumps from higher energy levels to n is equals to 5. Say this is n is equals to 1 and n is equals to 2, n is equals to 3 and n is equals to 4, n is equals to 5, and it is 6, 7, 8, 9th. Okay, so I repeat once again, when excited electron transition takes place from higher energy levels to n is equals to 5, that is 5th energy level, 5th orbit. Okay, so the emission radiation of the corresponding spectral lines were found in far infrared region. They were found in far infrared region. Okay, that is, they were found in far infrared IR, far infrared region of hydrogen atomic spectra. Far infrared region of hydrogen atomic spectra. Far infrared region of hydrogen atomic spectra. The series of that spectral lines are named as Fund series. They are named as Fund series. They are named as Fund series, like this: Lyman series, Balmer series, Paschen series, bracket series and Fund series. I will write here. So at first orbit, Lyman series is formed. Lyman series is formed. At second orbit, Balmer series is formed. And at third orbit, Paschen series is formed. Fourth orbit, bracket series is formed. Fifth orbit, Fund series is formed. So we described all 5 series, how they are formed. Okay, that is one. So that formation of the series. Now coming to the very important point. See, in any series, see how the series, see sir, we have how to identify the different spectral lines. The different spectral lines are identified by a special terminology. Okay, that is, say for example, like first line, say for example Balmer series, first line, second line, third line, fourth line. Okay, so that is, we can identify the various spectral lines by a special terminology that is called, that is H alpha, H beta, H gamma and H delta. So the various spectral lines are identified by the characteristic symbols. Okay, so now in any series, the concept is applicable to all the series. In any series, the first line, in any series, the first line, what is the meaning of first line? The very next excited level to that series. The very first excited level to that series. The very first excited level to that series. Got it? Concentrate. Now, in Lyman series, so to which level the electron is coming? The electron is coming from higher energy levels to second orbit. Higher energy levels to second orbit. That means the ground state for Balmer series is second, n is equals to 2. For Balmer series, n is equals to 2 because it is forming at second energy level. Okay, so that is the ground state. What is the next level to that 2? N is equals to 2, that is third orbit. So that is why 3 to 2 is the first line in Balmer series. Example, I am taking Balmer series. In Balmer series, first line in Balmer series, first line means, what is the meaning of the first line? The electron is, that is ground state. First line means N1 is equals to ground state is 2 because it is coming to second orbit, and N2 is equals to the excited level, that is the next excited level, that is third orbit. The electron is coming from third orbit to second orbit, that is called H alpha. This line is designated as H alpha spectral line in Balmer series. The very first line in the series is the next excited level. The electron is coming from the next excited level to that ground state. Okay, the point should be clearly understood because it is very, very important point. Okay, that means in Balmer series H alpha. So the electron is coming from third orbit to second orbit, that is H alpha spectral line. Now the electron is coming from fourth orbit to second orbit, that is H beta. Fourth orbit to second orbit, that is H beta spectral line. Fourth orbit to second orbit, that is H beta spectral line. Similarly, fifth orbit to second orbit, that is H gamma spectral line. Fifth orbit to second orbit, that is H gamma spectral line. Okay, and similarly the electron is coming from sixth orbit to second orbit, that is H delta spectral line. So in this terminology is applicable for all the series. The very first line in the series is called H alpha, second line is H beta, third line is H gamma, and fourth line is H delta. Similarly here also it is H alpha, H beta, H gamma, and it is H delta. Okay, these are the terminology to identify the various spectral lines with H alpha, H beta, H gamma, and H delta. That means identification of the various spectral lines with H alpha, H beta, H gamma, H delta. See, in the examination, in the competitive examinations, calculate the wave number of H beta spectral line in the Balmer series. They will ask you H beta spectral line in the Balmer series. So to understand what is H beta spectral line, H beta means, so we can understand that the electron is coming from fourth orbit to second orbit. That means N1 is equals to 2 and N2 is equals to, it is coming from fourth orbit. Okay, so that is the terminology in hydrogen spectra. Okay, in the next session 10th, that we will discuss about some more information about the hydrogen spectra.